In this series, we're going over every hard data analysis and problem solving question on the SAT. This is part 3, going over every hard question related to one variable data. All the questions here will be hard difficulty, means that's 3 out of 3 if you look on the SAT Online Question Bank. They're all the domain, problem solving, and data analysis. And the skill will be one variable data. They write : distributions and measures of center and spread. So one variable data, think of histograms, think of these box plots, so call those 5-point summaries, dot plots, things like that, where it just has to do with there's one variable that maybe it's always going to be the x-axis. Maybe it's a mass or test score or something like that. And then the y-axis will always be frequency. So there's only one actual variable, which would be the x data, and then you're comparing that, like how often does each of those happen. That's why histograms will be useful, box and whisker plots, things like that. All of these questions will have a unique question ID. If you look up in the top left for each question, it'll be there. And if you look in the video description, all of these question IDs will be listed along with the timestamp with the exact minute and second when I start going over that specific problem described by the question ID. And there will be a quick blurb that explains what the problem topic is. So if you want to look for a specific type of question to review those, then you can find that there. Diving right in, we've got a box plot or a 5-point summary, box and whisker plot, however you call it. It's showing the mass of group 1 and group 2. And just quickly looking at it, it looks like group 1 has a higher median mass, right? Their median is 25, whereas group 2 has a slightly lower, 24 as their median. But the spread is also wider on group 1. So if we look at the interquartile range, it ranges from 22 to 26, and the range as a whole goes from, 21 to 28, whereas section 2, the interquartile range is smaller. It's just going from 23 to 25, and the range of the entire thing is going from 22 to 28. So they have the same maximum, but the minimum is higher for group 2. So you could say group 1 has a higher central tendency, slightly higher, but it has higher variance or broader distribution. So let's look at this. The box plots summarize the masses in kilograms of two groups of gazelles. Based on the box plots, which of the following statements must be true? So again, we just listed off some of the things it could say. It could say they have the same maximum. It could say that there's more variation or a broader distribution, something like that, in group 1 than group 2. It could say group 1 has a higher median, because these are percentiles. They do the 0th percentile, 25th percentile, 50th percentile, 75th, 100th. But that's what the box and whisker plot is. Wherever this line is, that's your median, 50th percentile. Interquartile range means between 25th percentile and 75th percentile. So it's like the middle half of the data. And then the top 25% goes up to the maximum, which would be the 100th percentile. And I'm writing percent, it should be percentile. And then down here would be the minimum value, right? You could write that as 0th percentile. They also call this sometimes Q1, Q2, Q3, Q4. So the interquartile range is between Q1 and Q3. I don't know if they say Q0. I guess you could consider that. Usually just say the minimum. Same thing with Q4. I mean, a lot of times call that the maximum. So the mean mass of group 1 is greater than the mean mass of group 2. So we don't actually know the mean from this, right? Because the mean is adding up all of those values and then dividing by the number of things. And the fact that they have different distributions means that we really can't extrapolate that. Like you could say maybe the fact that this one seems to have more outliers and this one has like these outliers over here on the lower end. So that could skew the data to the left, even though the median value is higher, might have a lower mean or the same mean, something like that. So we don't know the mean. So whenever they have a box and whisker plot, try to avoid the ones that say mean. The mean mass of group 1 is less than the mean mass of group 2. And that could be true, but we don't know from the data. You'd have to actually have a table of all the values to find it, or they'd have to give us the mean in some way. If it was like an actual normal distribution, then you could assume that the median would be the same as the mean, but not the case here. The median mass of group 1 is greater than the median mass of group 2. So that is this line here, right? The middle of the box, in the middle of the box. The median for this one is 25, which is greater than 24, the median for group 2. So that would be true. The median mass of group 1 is less. No, 25 is not less than 24. So if they give you a box and whisker plot and then they ask you something about the central tendency, note that all you know from that plot, well, the only thing you know about the central tendency is the median, not the mean. So that would be C. Dataset A consists of 10 positive integers less than 60. The list shown gives 9 of the integers from dataset A. So we're missing 1 of those 10. The mean of these 9 integers is 42. If the mean of the data set A is an integer that is greater than 42, what is the value of the largest integer from data set A? Basically, what that would mean is when you add in the 10th point, it's raising the mean. So the mean of the data set as a whole is greater than 42. So that 10th number has to be bigger than 42. What is the value of the largest integer from data set A? What we know about the data set as a whole is the integers are all less than 60. Integer means that think of it as a whole number in this case. I guess you could also have a negative number that has no decimal, no fraction. It's a number that doesn't include a decimal, doesn't include a fraction. It's just a whole number or the additive inverse of a whole number. So a negative whole number. In this case, I don't think we have to worry about negatives because we know it's bigger than 42. So we know the average of these is 42, which we can confirm by adding them up, dividing by 9. And that average goes up when you add in the 10th thing, so it's going to be bigger than 42. When you add in that number, it has to raise it to something that greater than 42 that is an integer, right? The mean is also an integer. So the mean could be 43, 44. I assume it's going to end up being 43. Maybe that's the only one that will work if this is 60. But let's test this out. What is the value of the largest integer from the data set? So as of right now, that would be 46. But we'll see if the integer we have to add would be more than 46. I'm guessing it will be. We got 43 plus 45 plus 44 plus 43 plus 38 plus 39 plus 40 plus 46 plus 40. That's the 9 integers they gave us. It should have an average of 42. So they should add up to 42 times 9, which is 378. And they do add up to 378. And then when you add in that last integer, so 378 plus x, you'd have to divide it by 10. This whole thing needs to be equal to an integer greater than 42. And we know x has to be less than 60. It doesn't say less than or equal to, it's less than 60. So, just looking at it, to make it so it's going to be a multiple of 10, you have to add something that ends in 2. We know we're adding something that's bigger than 42. So if you added 42, then that would make it into, 378 plus 42 is 420, divided by 10 is 42. So yeah, if you add 42, the average would still be 42. So let's add something again. This has got to divide, this whole thing has to divide to make an integer. So we need this to add up to a multiple of 10, the numerator. So let's add 52. 378 plus 52 gives us 430. So that'd be 430 divided by 10 would be 43. And the reason we can't do 62, 62 is greater than 60. So that would not satisfy the fact that x is less than 60. So we know that 10th integer has to be 52. 52 is bigger than all the other values. The next biggest was 46. So 52 would be your answer there. All right, that one's a little bit tricky because you do have to, kind of think a little bit. It's not just setting up an equation and solving. We have to think, how could you make this into an integer? It's more of a number theory thing. And then keep track of that thing they had at the end. So it's kind of a reading comprehension mixed with number theory. And then once you get 52, make sure, plug it back in, add these all up, and they add up to 430. If you divide that by 10, the average is 43, which is an integer greater than 42. So adding that in, raise the mean to greater than 42. It's an integer. That's a number that's less than 60. So that satisfies it. You can't think of another number that will work because that's the only one. Data set A and data set B each consist of 27 values. The table shows the frequencies of the values for each data set. Which of the following statements best compares the means of the two data sets? We've got the frequencies for each thing. If we want to find the means, what you do is just figure out for each one what's the sum of all these things and then divide by the number of values. Each of them has 27 values. They did say that. So we could say the sum of the values in A and the sum of the values in B. I know that's not really proper notation, but this is the sum sign. So I'll just say sum of A values. This would be sum of B values. And we can compare them. So to do that, we'll do the value times the number of those values, to find the sum. Sum of A values, 30 times 2 gives us 60. 34 times 4 would give us 136. 38 times 5 would give us 190. 42 times 7 is 294. And then 46 times 9, 414. So now we just add up all of these values. So 414 plus 294 plus 190 plus 136 plus 60 gives us 1,094. We're dividing that by 27 to find the mean. And that is equal to 40.518518, so like that. Then we've got this next one. So same thing, we're multiplying the value by the frequency of that value. So 30 times 9 would give us 270. 34 times 7, that gives us 238. And we've got 5 times 38, which is 190. Then we've got 4 times 42, which is 168. Could have done that one probably without a calculator. And then 46 times 2 is 92. Add all these up, 92 plus 168 plus 190 plus 238 plus 270 is 958. So we have 958 for the sum of the values in B. Divide that by 27. Now, even before you divide, you can see the mean is going to be less for B, right? If the sum is less than B and they have the same number of values, but let's just find the actual mean. Divide that by 27 gives us the mean of B is equal to 35.481, like that. So both of them have repeating decimals, but the mean of dataset A is greater than the mean of dataset B. That's true. 40.518 is bigger than 35.481. So that looks good. The mean of dataset A is less than the mean of dataset B. That's not that. The mean of dataset A is equal. No, they're not the same mean. There's not enough information to find the means. There is now, right? They didn't actually, you had to calculate the mean, but you can find all of the values based on this, right? All of the 27 values are in some way listed here based on the frequency of each value. It's not like we knew this was, if this was between 30 and 33, and this was between 34 and 37, something like that, then you would not be able to do this because you wouldn't know where in that value it is. You could still kind of estimate the mean, but to find the mean, you need to know the actual values. But these are like the exact values of these two. These are the values of these four, and so on. So we're able to find the sum. And then again, we didn't even have to actually divide them by 27. You could have just compared the sums. And also, if we look at it, it makes sense. Like if this one has a lot more of the smaller numbers and fewer of the bigger numbers, this one has more of the bigger numbers, fewer of the smaller numbers, then just eyeballing it, you go, okay, this one's going to have a bigger mean. This one's going to have a smaller mean because they're concentrating around the higher value. They're concentrating around the lower value. A data set of 27 different numbers has a mean of 33 and a median of 33. So the middle value is 33 when they're listed in increasing order or decreasing order. And the mean would be when you add up those 27 values and then divide by 27, the number of values, it gives you 33. So a new data set is created by adding 7 to each number in the original data set that is greater than the median and subtracting 7 from each number in the original data set that is less than the median. Which of the following measures does not have the same value in both the original and new data sets? Think about, for the median, it stayed the same. Like the median is still the middle value, or you increased all of the ones that are above it, you decreased all the ones that were below it, but this value didn't have anything added or subtracted from it, and it is still the middle value. These ones just went further to the right, these ones went further to the left, this one's still the middle. So the median did not change. The mean also wouldn't change because it's 27 values, so there's only one value in the middle. Think about like there are 13 over here and 13 over here. All of the 13 on the left, like the 13 that are less than the mean, had 7 subtracted from them. So you could basically multiply that by 13 times -7. And then over here, all of them had 7 added. So it's 13 times 7. So if you add 13 times -7 and 13 times +7, those cancel out. Right? These would be like additive inverses, what you added and what you subtracted, they completely cancel out. Or you could think of like matching each one up, like the +7 matches with the -7, the net 0, +7 matches with the -7. So either way, the median and the mean did not change. The sum of the numbers also wouldn't change. The sum and the mean would be the same thing. So just we know, right, the fact that these are both options means that it must not be the correct answer because the mean is calculated by doing the sum and then dividing by the number of numbers. So if the mean doesn't change, the sum doesn't change, the sum doesn't change, the mean doesn't change. The standard deviation, that has to do with how spread out they are from the mean. While the means stay the same, the numbers are further from the mean on average. All of them are 7 further than they were before. The standard deviation, if they had done something like the IQR, the interquartile range, or some other measure of spread, the range, then that would increase. The standard deviation is the only one of these that has to do with the spread of the data. The other ones are all central tendency. Some of the numbers, I guess, that's just a data point related directly to the mean. The 2 box plots show the distribution of numbers of books read over the summer by the students in 2 different English classes. What is the positive difference between the ranges of number of books read over the summer for the 2 classes? So the positive difference, when you say that, some students are like, I don't know what positive difference means. It just means basically how far apart are the numbers, or you could think like when you subtract one number from the other, make sure you're subtracting the small one from the big one, or just if you do subtract the big one from the small one, it gives you a negative number, so just make that positive, right? So because difference, we're taught difference means subtraction, but if you said, oh, like, what's the difference between 2 and 10? Most people know that means 8, right? It's how far apart they are, but if you did 2 minus 10, that gives you -8. So when they say positive difference, they just mean, give me 8, don't give me -8. Okay, so don't get thrown off by that. Between the ranges of the number of books read over the summer. So the range just means the maximum minus the minimum. So like, what's this, basically how spread out are the extremes? And this one goes, someone read 0 in that class, and then someone read 5. So the range of class A is 5, and then for B, the lowest was 1, and the highest was 10. So 1 to 10, that's a difference of 9. So the range of B is 9, the range of A is 5, so you just subtract 5 from 9, it gives you 4. The difference in the ranges would be 4, and that is a positive number. The dot plots represent the distributions of values in datasets A and B. which of the following statements must be true? The median of dataset A is equal to the median of dataset B. The standard deviation of dataset A is equal to the standard deviation of dataset B. So before I even look at them closely, the median, we can actually find that by figuring out what the middlemost value is, because dot plots, right? It's kind of like they listed them all out. I'll show you how to find that in a second. So that one we can either confirm whether it is or is not true. For standard deviation, so we don't actually need to calculate the standard deviation. Now, it might be something that's valuable to understand how that formula works, make sure that you've at least seen it before. It has to do with like your, finding the difference from each point to the mean value, which first you'd have to find what the mean is, not the median. And then you're like squaring all of those differences. The reason you square it is to make sure that none of them are negative. Then sum all those squares and then do the square root of the whole thing. You don't need to know the formula from the top of your head. You probably won't even need to use it on the SAT. But the main thing you're understanding is it has to do with how spread out the data are. And for them to have the exact same standard deviation, for them to be, what is it, the standard deviation is equal, then pretty much they should look like the same shape. So like if you found like the middle value, like this one should be this one should be two-way, this one should be two-way, right? So it should look basically identical, just maybe moved over to a different spot. And just taking a little look at it right now, it doesn't seem to be the case. Now, because it's not, that does mean like to feel confident in your answer, you might have to actually calculate the standard deviation. Or I'll actually show you how to do it on Desmos, because you get a Desmos calculator on this test. And I mean, I really don't think it's worth, even if it's worth knowing how to calculate standard deviation by hand, it's not worth that time on the test. What do they say how many data points there are? No, we have to count.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17.
So there's 17 data points. Now it looks pretty symmetrical. So you could just figure out like, okay, this is going to be the middle one. But we know there's 17 data points. That means there's 8 on the left, 8 on the right. So we're looking for like the 9th data point. So you go 1, 2, 3, 4, 5, 6, 7, 8, 9. And then there should be 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So the middle of this one is 13. That's your median. And then for this one, is it also symmetrical? Yeah, I think it's also symmetrical. So it's also going to be 13. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, then 1, 2, 3, 4, 5, 6, 7, 8. So the middle value, if it's an odd number, literally the median is just going to be the middle value. If they're an even number of points, then the median, if they're not the same thing, like in this case, like they're both 13. I mean, there was an odd number of points, but say you took one of these points out. If they're both 13, then it's still the median. Or if they're two different numbers, say you have like 12 and 13, then the median would be 12.5. If I like say this was the 10th term, this was the 11th term out of 20 total terms. But luckily they gave us an odd number of values, so we don't even think about that. So they do have the same median. So we know 1 is definitely true. So we can cross off B and D. And now it just has to do with, are they spread the same way? I mean, just looking at it, they're clearly not spread the same. So I know I said you could calculate the standard deviation, and I guess I'll show you how you can do that if you just want to feel 100% confident. It's really kind of a waste of time in this problem because you can see they're a symmetrical distribution, right? It's the same distance, like each point that's over here has a point that matches the same distance over here, which means that the mean will be the same as the median for this. Same thing over here. But you can see like in this one, these 2 points are the same as the mean or the median. In this one, you have the same thing. So it's 1 and then 2, it's 1 and then 2 and then 4. But then these points that were together with the mean, like the same as the mean, are instead moved to here and to here. Right, so it's just going to be further apart. So other than that, they're the same, but they do have these 2 points that are further apart, which are going to increase the standard deviation pretty significantly. Right, because you're going from like something that looks like that to instead something that looks more like that. Spread out from the center, you want it to be grouped at the center. I mean, that would be a low standard deviation if they're grouped near the center. Whereas if they're grouped away from the center, they call that a disruptive distribution pattern, then it would be a higher standard deviation. So I already know 2 is not true, which means that it's just going to be 1 only. But as I promised, I'll show like how to calculate the standard deviation. You open Desmos, and then you're going to type in the values. So in this case, we could say there's 10, then 4 11s, then 2 12s, then 3 13s. So what we're going to do for one variable data, you don't use a table. We're just converting that dot plot into a list. To start a list, click here, this part that says ABC, and click a bracket. You can see empty list. It's empty because we haven't typed anything into it yet. Now you just type in the value. So for that first dot plot, it had 1 10, and then it had 4 11s, and then it had 2 12s. So you'd write 12, comma, 12, and then it had 3 13s, and then it had 2 14s, and then it had 4 15s, and then it had 1 16. All right, so that's the 17 element list. And now you could set this equal to something. So say we want to say this is like list A. So we could say A is equal to this. Now, if we want to do the statistics of this, for one, like you could do the median A like that, and it'll give you it's 13. Right? That's what we found as well when we just did it, counting them out. That's just showing like if you just type them directly into Desmos, if you knew to do that right away, it doesn't take that long to do. Just make sure you type them accurately. It could give you the median. It could even, if you go here, I think you could just do stats A, and it'll give you all of this stuff. It gives you the min, median, interquartile range, or if you want, you could even make it into a dot plot. You could even, if you want to confirm that you typed it in right, just make a dot plot out of it, right? That's the same thing that we had there. So dot plot of A. They can also make, let's see if we go back here. They could even make a histogram or a box plot. So box plot of A, look like this. So all these are interesting little things that you could do with it. Now, what we wanted to find was the standard deviation. I always tell my students, the function that they have in here is stdev, which a lot of them found funny because it sounds like something you learn about in health class, but it's not stdev. Standard is st, and then dev is deviation. So stdev of A gives you 1.83711. Now, that doesn't really give us much information. We're using it more just to compare it to list B. So now I'll just type in B, and B was very similar. Again, we already know that B is going to be a higher standard deviation because it's more spread out. Like the dots, you would just be moving this dot here and this dot here. Whatever, we have to do the same thing where we put the brackets, open bracket like that, and now we just type in our values. So B is meant to have, and let's shrink myself down here. It's supposed to have 2 10s instead of 1 10. And then still 4 11s, and still 2 12s. And instead of 3 13s, it's just 1 13. And then, symmetrical, so 2 14s, still 4 15s. And then again, instead of 1 16, it's going to be 2 16s. 16, 16. All right, so now we could do the dot plot of this, so dot plot of B. And that's just the 1 is giving you the width of the element. I don't think we need to type that in though. Like that. If you click this green box here, this green circle there, it gets rid of that first dot plot where it's not plotted. So now we can see what this looks like, right? It was like that. And then we're switching to a little bit more spread out. And now if you want to find the standard deviation of that, you write stdev, or you can go to statistics, standard deviation of B. You can see this one is 2.12. So they're clearly not the same. Clearly B was a bigger standard deviation already. So you really don't need to use this, but if you feel comfortable doing it, just make sure you know for a list, for one variable stats, if you're doing a list, there's only one variable and then the frequency of them. You don't use a table, just write your brackets, assign some name to it, and then you can find all the stats for that, the min, Q1, median, Q3, max. You can also find the mean, you can find the interquartile range, all of that data is available there. You can make a dot plot and then the standard deviation. So this is something, again, make sure you're comfortable doing this. You don't need to do it because you can just look at the data and understand it. As long as you understand standard deviation has to do with the spread and just, from seeing this, these are the same except that you moved basically 2 that were at the center. So this point and this point, you moved them to be as far away as possible, which means you're making them more spread out. So the standard deviation will go up. If nothing else changed and then those 2 moved, it's making it more spread. Without using Desmos, you could solve it, but that's just how you would use Desmos to verify your answer to feel more confident. And, as long as you play around with Desmos before the test, don't do it for the first time on the day of the test, but as long as you've played around with it before and once you have something like this, all right, well, I'm just going to type these into Desmos, you can do it pretty quickly, so it won't really waste much time. All right, here we've got a table with weight in pounds and then frequency. The frequency table summarizes a data set of the weights rounded to the nearest pound of 71 tortoises. A weight of 39 pounds is added to the original data set, creating a new data set of the weights rounded to the nearest pound of 72 tortoises. So you had 71, you add one, 39 pounder. So the 39 pounds, that's not even on here, right? But 39, and there's a frequency of 1 for that one. So that would be an outlier. It's going to bring up the mean in a big way. Which statement best compares the mean and median of the new data set to the mean and median of the original data set? Well, first let's figure out what the median was. So there are 71 tortoises. So just think of it subtract 1 from it because the 1 is going to be your median. And then you've got 35 values that are less than that, 35 values that are greater than that. So we're trying to find basically the 36th value. And we got 32. So the 36th is going to be somewhere in here. Right? The median will be sandwiched between 2 numbers that are the same as the median. So 17 is your median. And when you add 1 up here, right? Even though that outlier is going to increase the mean, right? You're increasing the total, and then when you divide that by the number of 72 of tortoises that you've got, it will bring that mean up. But the middle value is still going to be 17, right? It'll be a different 17, or I guess it'll be the average of the 17 it was and then the one right above it, but there are already two 17s in a row there. So the median will stay at 17. So median, we could say the median at the beginning was 17 and at the end was 17. The mean will go up, right? We don't even need to know what it goes up to. Just think about, maybe you have a classroom of students and they're all like 15 or 16 years old, right? So 15 and 16, and then some teacher walks in who's like 90 years old. By going in there, the average age in the room just went way up because of that outlier, that one person. Now the middle age still probably stayed the same, but the mean will go way up with that one outlier. Same thing, if like a baby came in, then that would bring down the mean, wouldn't really change the median. That's generally the case. We verify that the median does stay the same at 17, and we know the mean is going to go up because, again, we added an extreme high value, which will increase the total by a lot, and then more than just what the mean is. A says the mean of the new data set is greater than the mean of the original data set. That part is true. And the median of the new data set is greater than the median. That is not true. Right? The medians stay the same. So we know it's not A. Next, we've got the mean of the new data set is greater than the mean of the original data set. That's true. And the medians of the two data sets are equal. Right? They're both 17. That seems like the right answer. So it's B. Let's just cross out the other ones, see why they're wrong. The mean of the new data set is less than the mean. So if you add a really high extreme value, that's not going to decrease the mean. Now, if we added one that weighed 1 pound, that would decrease the mean, right? Really, if you add anything lower than the mean to the value, then that would slightly decrease the mean. But if we added an extreme value, an outlier in the upper end, it's skewing the data to the right, which skewing will affect the mean and the standard deviation more than anything. And it's not that. The mean of the new data set is less. Again, it's not less. So we can cross that out even without reading the second part. But we do know the medians are the same. The mean went up. The table shown summarizes the number of employees at each of the 17 restaurants in town. Which of the following could be the median number of employees for the restaurants in the town? The reason they say could is because they don't have the actual values, they're just ranges, or I guess you could say more like domains or something. But we know, we can figure out which range it's going to be in because these are ordered in increasing number of employees for the ranges here. There are 17 total restaurants. We want to find the middle number of 17. Think of take one away because that's going to be your median value, and that leaves you 16. So half of those, which half of 16 is 8, will go less than the median. Half of them, 8, will go above the median. So we're looking for the 9th value, right? The 9th value, so we got 1, 2, plus 4 is 6, 6 plus 2 is 8. So the 9th value is going to be in this range. It's going to be the bottom of this one. So from 20 to 25. Number of employees. So that means it also happens to be the mode. That doesn't really affect the fact that that's the median. So it's somewhere between 20 and 25, likely on the lower end of that, but I don't think that's going to matter. So 2, we know it's not 2. We know it's not 9. We know it's not 15. Because that would put them in these ranges. It's got to be in this range. That's where the median is going to fall, the 9th value. So 21, it's on the lower end of 20 to 25, so that does fit, and it makes sense as well. All right, we've got data set A, data set B. We've got 2 histograms. Although neither of them has a bell shape, both of them just go up like that. 2 data sets of 23 integers, each are summarized in the histograms shown. For each of the histograms, the first interval represents the frequency of integers greater than or equal to 10, but less than 20. The second interval represents the frequency of integers greater than or equal to 20, but less than 30, and so on. What is the smallest possible difference between the mean of data set A and the mean of data set B? This is another one where the reason that they're saying possible, smallest possible, is because these are ranges. So we don't know the exact values. We can't figure out what the mean of each one. We just kind of estimate it or figure out what the smallest would be. So the smallest possible difference basically means, right, even if this could have been 21 and this one could have been like 29, so that could be like an extra 8 divided by the number of things apart for each one. Just assume that all the values are the same within these. So it says it's greater than or equal to that number. So this could be anywhere from 20 to 29. This could anywhere from 30 to 39 and so on. All right, well, if we look at this, they're basically the same graph. This is like 3, then 4, then 7, then 9, just shifted to the right by, it seems like by 10, but if we're trying to find the minimum, right? So basically the frequency of 20 to 30 for data set A is the same as the frequency from 10 to 20 of data set B. The frequency of 30 to 40 is the same for A as the 20 to 30 for B, and so on. So they all will match up like that, which makes you think it's just going to be 10, right? That the difference is 10. But since we're trying to find the smallest possible one, these integers could all be 19, and that technically follows the rule. These could all be 29, and that follows the rule. These could all be 39, these could all be 49. Unlikely, but that is possible. Right? That's not against the stipulations they gave. Similarly, these could all be 20, and these could all be 30, and these could all be 40 exactly, and these could all be 50 exactly. So even if these are all just, like every point in this data set is just one higher, if they happen to line up in this way, that could be true. And then that would mean the mean, if every point is shifted up by 1, the mean is just shifted up by 1. So while your instincts, you hopefully will immediately eliminate 0 and 23. 0 would mean that they're the same. They're not the same. 23, right, like I don't even think that would actually be possible for this. Right? I think it has to be somewhere between 1 and, I guess, 19. I guess if these were all 11 and these were all 29 and so on, it could be 18. So 18 is like the maximum difference in the means, and that'd be very unlikely. Just like 1 is unlikely, but 1 is technically the lowest possible difference. 10 would be what you expect the difference in means to be, but they want the smallest possible difference. This one's a little bit tricky, but just think of it that way. Like it's trying to show that with these ranges, you can't find the exact mean. There's a pretty large range of possible means because you don't know that it's evenly distributed within each of these ranges. We've got a table with values and frequencies, but the frequencies are all represented by variables, so all A's or 2A's or 3A's. The frequency distribution above summarizes a set of data. It says the frequency distribution above summarizes a set of data where A is a positive integer. So I think the main reason they're saying that the positive integers, just so you know it's not 0, like you can't have negative things, but we know A is not 0, so it's an actual number. How much greater is the mean of the set of data than the median? Just at first glance, it looks like they'll be the same. Looks like they'll be the same because it doesn't matter what A is. We could treat A as if it's 1. We could treat A as if it's a million. But obviously, it's easier to write out if it's 1. It's basically like we have 1, 1, and or however many 1s we have. We have twice as many 2s. And however many 1s we had, we have 3 times as many 3s. And however many 1s we had, we have twice as many 4s, is that number of 1s. And however many 1s we have the same number of 5s. So it's like this. And now if we look at this, like the median will just be the middle number, that's this 3. And also, it's symmetrical. Right? This would be, if you graphed it, it's completely symmetrical in terms of, right? There's a 3 here, there's 3 here. To get down to 2 from 3, from the median, or it's what's going to end up being the mean, you have to go -1, and then to go up to 4, +1, -1, +1, -2, +2. So everything that you subtracted from the 3's, you also added on the other side, which means that it's going to be a net change of 0. So it's like if we added up a bunch of 3's here. All right, so the mean is the same as the median. They're both, in this case, 3. And it doesn't matter, right, if A was 2 or if A was 10 or something like that, right, it's still the same principle stands where like you'll have the same numbers or the same distance away from the center down here and up here. So how much greater is the mean of the set than the median? 0. They're the same. Okay, so this one, it seems like it's going to be tricky because they have these A's and stuff, but again, a lot of times if they're throwing in something that seems out of the norm, that means that the actual math involved will be easy. You just have to conceptualize it a little bit better. And it wants to make sure that you actually understand what mean and what median like represent in a data set, not just memorizing the formulas and plugging it in. 2 different teams consisting of 10 members each ran in a race. Each member's completion time of the race was recorded. The mean of the completion times for each team was calculated and is shown below. So we got Team A, 3.41 minutes, and Team B, 3.79 minutes. Which of the following must be true? Every member of Team A completed the race in less time than any member of Team B. That's not necessarily true, right? The slowest on A was likely slower than the fastest on B. It's just the average just worked out that way. The median time it took the members of Team B to complete the race is greater than the median time it took the members of Team A to complete the race. That's also not necessarily true. They didn't say anything about if there are outliers or anything. So if you had a really fast runner, like maybe you had like a world-class runner on Team A, they could be an outlier that will bring their mean down, even if like all of their other people were slower than like the normal people on B, or like just as long as their middle person was slower than the middle person on B. So it could be maybe A had like a couple of really, really fast people bringing down the average, Or on the other hand, maybe B had a couple people who were really slow and they brought the average way up. I think that's actually easier to have because one person could, take unlimited time, right? The fastest you can go is set by, some people say, the fastest possible time is 0, but physically that's not even possible, right? There's some minimum amount of time someone could physically do something in, like even the fastest person alive. Whereas for how long it takes, if someone just decided to walk the entire time or take a break in the middle or something like that, they could take an hour if they wanted to. They probably would end the race before then. But that's what's very likely is maybe there's an outlier here that brought the mean up, but that doesn't change the median. The median is just the middle person. So I guess it's going to be the average of the 5th and the 6th person if there are 10 members per team. So we don't know what the mean is. We don't know what the median is. We don't even know how they compare. There is at least one member of Team B who took more time to complete the race than some member of Team A. Okay, well that we do know. Because if every member of Team B went faster than every member of Team A, then there's no way Team A has a faster time. Right now, again, it could be like 1 or 2 people carrying the team and bringing the average way down for one or bringing the average way up for the other. But this is saying at least one member of Team B took more time to complete than a member of Team A. The opposite of that, if that's not true, that means every member of Team B beat every single, even the fastest member of Team A, which can't be true if they lost the race, right? That wouldn't make any sense. So 3 is the only one that has to be true. 3 is the only one that has to be true. 1 and 2 could be true, but we don't know from the information they gave us. So 3 only, 1 and 2, we don't know. The mean score of 8 players in a basketball game was 14.5 points. If the highest individual score is removed, the mean score of the remaining 7 players becomes 12 points. What was the highest score? The way that you do this is you just figure out what the total points are of the 8 players with the highest score included, and then find what the total points would be for the players without that higher score, and then you figure out the difference, and that difference is accounted for by that player, like how much they scored. In this case, we would do 8 times 14.5, which give us 8 times 14.5 is 116. So the entire team scored 116, including all 8 players. And then when you remove that highest scoring player, so 7 times the average of those ones, 7 times 12 would give us 84. So now you just find the difference between the team's points with the player and without them. So 116 minus 84, which would be 32. So 32 points scored by that player. And you could also think of it as basically, right, the average was 12. It went down from 14.5. So this is like 7 players. They don't all have 12 points, but you could think of it essentially as there are like 7 players who got 12 points. So if you add in 32 to that, then the average should go up to 14.5. But you also think of like if there were 8 players that got 12, so 12, 12, 12, 12, then how much you have to add to each one to bring the average up? 2.5 to each one, which 32 is 20 more than 12. So basically, they scored 12 to be the same as everyone else, and then they had 20 more points that you could distribute between those 8, and 20 divided by 8 is 2.5. So, and that's another way that you check it. I would just do it this normal way. Find the total with the player, find the total without the player, subtract those. The difference is 32. All right, here we have the dot plot represents a data set of the number of bursts for 13 eruptions of a steam vent. So I guess like each point is an eruption, and like the number of bursts is where it is on here. Okay. So there were 13, and then it says if an additional eruption with 11 bursts, so we're adding one that's going to be an outlier all the way up here. It's up at 11, and there's just one of them, is added to this data set to create a new data set of 14 eruptions. So the 13 that are plotted there, the 13 dots plus this new dot at 11, which of the following measures will be greater for the new data set than for the original data set? All right, so for the new one, greater for the new one. So which one is brought up? Well, the options are the median number of bursts and the mean. Well, the mean will definitely be brought up because if you add in one value that's like an outlier in the upward bound direction, right? It's like adding to the total more than any other point, and then you divide it by the number of points, right? It's still going to go up. So anytime you add a value that's greater than the mean, and it's just like the one thing you add, then that will increase the mean. So even if, like, say the mean was 2 point something and you add 3, that would technically bring the mean slightly up. But if you add 11, that's going to bring the mean a lot more up. In this case, we know the mean will go up, but for the median, we have to figure out what the median is originally. So of the 13 eruptions, so 13, the middle term of a set of 13, like 13 values would be the seventh number. The way to do that is just you subtract 1. So 13 minus 1 is 12. And then half of 12 is 6. So that means you have to have 6 to the left, 6 to the right. So the seventh term would be the middle. Or you could do like plus 1 divided by 2 is going to be your median value is the seventh. But either way, the seventh value here, 1, 2, 3, 4, 5, 6, 7, is this 2, which means even if you add another one, then the new median would be the average of the seventh and the eighth term, which is still going to be just the average of 2 and 2 is still 2. So your median starts at 2 and then ends at 2. So the median does not change. This is, would it be greater? It won't be greater if it's the same. Right? It doesn't say greater or equal. So 1 is not true, 2 is true. So it's 2 only, not 1, not 1. It's not neither, because 2, the mean number of bursts increasing, is true. Each of the following frequency tables represents a data set. Which data set has the greatest mean? The way to calculate mean is just add up the values and then divide by the number of values. And to find the number of values, you have to add up the frequencies. So in this case, we got the easier way to add this is 4 plus 6 is 10, 10 plus 5 plus 7, that's 22. So there's 22 here. You can add all of these up, divide it by 22. Over here, you've got 4 6s. So add those up, it would be 24. If they did have the same number of values in each one, then you could just figure out which one is the highest total, like the highest sum. But that seems to not be the case here. 22, 24. Yeah, here it's even 2 more than that. So this would be 26. And here, what's 8 plus 5 is 13, times 2 is 26. So you could do the sums and then divide them by their respective values. So divide this sum by 22. And when I say sum, in this case, it'd be something like, not something like, it would be 70 times 4, right? Because you have 4 70s, plus 80 times 5, plus 90 times 6, plus 100 times 7. Add all of that up, then divide it by 22. That would give you your mean. Now you can do that for each one and compare it. But if we look at this, just when I was scrolling through, it looks like the other ones are very easy to find the mean, even without doing any like actual calculation. Because we can see this one is a uniform distribution, which means it's equal number of values for each of the values. So like if you graphed it, it won't be a bell curve. It's just going to be like a straight bar across 1, 2, 3. Like they're all of that same frequency of 6, which means they're equally weighted. And that gives us that the median and the mean, in this case we're using the mean, I believe, right? The mean is just going to be the middle value. So that'd be 85. Right? So we actually know, even without figuring out what the sum is to do this, your mean of this one is 85. And this one, even though it's not uniform, like a uniform distribution, they're equally spaced around this median, around this middle. Because you can see, right, the middle of 80 and 90 is still 85. And all of the ones that are 80s, you have to subtract 5 from that. So there's 6 values where you subtracted 5 from 85. And then there are also 6 where you added 5. So 6 times negative 5 plus 6 times positive 5, that cancels out. And then here, right, the 70s are 15 away from that median. And so are the 100s in the opposite direction. So you're adding 15 7 times to get the 100s. And then you're also subtracting 15 7 times. That will cancel out as well. So this one, the mean will also be 85. And it's the same thing down here where they're just all equidistant around that 85. So this is minus 5 plus 5 5 times, and then minus 15 8 times, plus 15 8 times. That'll cancel out. You're going to all sum to, right, that multiple of 85. 85 times 26 here, and 85 times 24 here. Now, if you want to just do this calculation to feel more comfortable about it, that's fine. But if these are all 85, for one, I already know the answer's got to be A, because you can't circle B, C, and D. But just looking at it, right, we've got here, most of the terms are above 85. Right? For every term that's 5 below it, we've got one that's 5 above it plus an extra one. And then for every term that's 15 below it, there are 4 of those, we've got actually 3 extra. So there are 4 terms that are 15 below and 7 that are 15 above. So this one we know is going to be greater than 85. And again, if you want to feel more comfortable with it, you just multiply this out. 70 times 4 is going to be 280, plus 80 times 5 is going to be 400, plus 90 times 6 will be 540, plus 700. That gives us 1920. So 1920 divided by the 22 values there gives us 87.27 repeating, which is greater than 85. So this one does have the greatest mean. Again, you can calculate all these, you'll get 85 for each one. But that's just a little trick. And I explained it. It took longer to explain it. But if you were comfortable to recognize that, like, they're probably not trying to make you do a bunch of just tedious math, because calculating means is not a super complicated thing, right? If this is a hard section, it's more just, is there some trick or pattern you could figure out to do this quickly so you have more time for the harder questions? Here we have the mean amount of time that the 20 employees of a construction company have worked for the company is 6.7 years. after one employee leaves the company, the mean amount of time that the remaining employees have worked for the company is reduced to 6.25 years. So that means that they had to have worked longer, which makes sense. Usually someone leaving is maybe they're retiring, they've been there for a long time, or they've just worked there for a while and want to work somewhere else. But yeah, so if the mean went down when they left, then they had to have a value that was greater than not just the new mean, but then the original mean, because they were bringing that mean up. Looks like they're bringing it up by 0.45 years, which is pretty significant with 20 employees. To like each person, like each year that you're there, you're only bringing it up a 20th of a year, so 0.05. So, I mean, they're probably there a lot of years. We know it's greater than 6.7 though, so we can immediately eliminate A and B. And just looking at it, it looks like it's probably going to be D, because that one is significantly greater, and it needs to be quite a bit greater. 9 is only, 2.3 greater? I don't think being 2.3 years greater than that would be enough to bring it up. But, that would just be a way you could find it in a rush. It's not too long. It doesn't take too long to do this one anyway, though. You figure out what are the total years worked with that employee there. So 20 times 6.7, that's the total with all 20 employees. 20 times 6.7 gives us 134 years were worked between the entire staff at that point. Then after the person leaves, there are only 19 employees, and their average is 6.25. So 19 times 16, times 6.25 gives us 118.75. So now you just find the difference between these two. So 134 minus 118.75, and that gives us 15.25. So 15.25D is your answer. The dot plot represents the 15 values in dataset A. Okay, so this is dataset A right here. Dataset B is created by adding 56 to each of the values. I thought it was going to be adding an outlier all the way up here, but adding 56 to each of the values in dataset A. So each one is just getting shifted up by 56. You could basically just, if these points, I'll actually show an interesting way to visualize this. So if each of these points is here, 1, 2, 3, 4, 1, 2, or 1, 2, 3, 4, 5, 1, 2, 3, 4, 1, 2, 3, 1, 2, and 1 there. It's just you're taking all of these data points, so all 15 values, and we are shifting them up by 56. So there'll be, instead of having a minimum of 22, it'd be 22 plus 56, that'd be 78. Instead of having a maximum of 26, it'd go 26 plus 56, which would be, 82, like that. Right, whatever the middle was will stay at the middle. So they're still equally spread out. It's the same shape the data is forming there. If you graphed it as a histogram, it'd be the same shape of it's not really a bell curve here. It's more like this. Right, it'd be the same thing, just shifted over by 56. Which of the following correctly compares the medians and the ranges of the data set A and B? Before we look at it, the median just went up by 56, right? Every single value went up by 56. So the mean also went up by 56. But whatever the middle value, let's see, 15, that's going to be the 8th term, because there's 7 less than it, 7 greater than it. So 1, 2, 3, 4, 5, 6, 7, 8. So at this point, 23 was your median. Now it's this point at 79. And so it just shifted up by 56 like every point did. So the median will go up, and the range stayed the same. Range is just the difference between the smallest value and the biggest value. It's one of those measures of variance, or like the spread of the data. The data is no more spread out than it was. Like from the smallest to the biggest, that's still a difference of 4. 78 to 82 is 4. 22 to 26 is 4. So the range did not change. The ranges are equal between this two, dataset A and dataset B, but the median went up by 56. So the median of dataset B is equal. No, they're not equal. So it's not that part. The median of dataset B is equal, again, they're doing that, to median of dataset A. That's not true. The median of dataset B is greater than the median of dataset A. So B is greater, that makes sense. It's greater by 56. And the range of the dataset B is equal to the range of dataset A. Okay, as we said, the range didn't change. The range is still 4. So that'd be C. And just, let's see why D is wrong. It's probably just going to say the range is not equal. The median of dataset B is greater than the median of dataset A. Good. The range of dataset B is greater. No, it's not. They're the same range. Right? The range didn't change. You just shifted that data up. So it's not D. The answer would be C. And here we have dataset A consists of the heights of 75 objects and has a mean of 25 meters. So dataset A, there are 75 objects and the average or the mean equals 25 meters. So dataset B consists of the heights of 50 objects and has a mean of 65 meters. Dataset C consists of the heights of the 125 objects from dataset A and B. So you're just combining the two. Main thing to watch for here, you can't just do the average of the two means, right? It's not just 25 plus 65 divided by 2, because there are a lot more objects in A. Like you could do that if they had the same number of objects, but you would either have to weight it. So by weighted, I mean like, all right, of the total objects, it's going to be 75 out of 125. That's the proportion of them that have this average. So multiply that by 25, and then add that to the proportion of them that have the 65 average. So it's 50 out of 125 times the average of those objects. So you could do it like this. I mean, this is an odd way to set it up, but this will get you the right answer. The other way you could do it is just figure out what the total height of these objects is. So that's just going to be 75 times 25, and add that with the total height of these objects. So it'd be the 50 objects times 65, the average for those 50. Right? So it's going to be the total height for these, total height for these. Add them up, it's the sum total height of all of them, and then divide that by the number of total objects, 125. Right, so either of these will get you the same answer. I'll do it this second way first. 75 times 25 plus 50 times 65 gives us a total height 5125 for all 125 objects. Divide that by the number of objects, divide by 125, gives us 41. All right, so 41 should be our answer. And now just to verify it with this other method, you do, okay, 75 over 125 times 25 gives us 15. So it's 15 plus 50 over 125 times 65 equals 26. And 15 plus 26 is 41. So you get the same answer both ways. You really only have to do one of those ways. I would do this one that I wrote, like I did it first, but like I wrote it down here below the other one. But again, either way will get you the same answer, 41. Data set F consists of 55 integers between 170 and 290. Okay, so if we graphed it on like a histogram, be 170 to 290 like that. It doesn't say what the distribution is yet, but there are 55 integers. Dataset G consists of all the integers in dataset F as well as the integer 10. Okay, so you have all of these plus 10. So I don't know, say it looks like that or something, I don't know. And then we're adding in 10, which would be way down there. So let's see, this is dataset F. And then when you add this in, G is this plus all these. Which of the following must be less for dataset F than for dataset G? So less for F than for G. Okay, well we know G is adding this outlier down here, so that's going to bring the mean like pretty significantly down. I mean, what are the 55 integers? So maybe like a couple of values down because it's so much lower than everything else. Now that would mean that G is lower. They say which must be less for F. So F has the higher mean, right? F's mean, we could write that mean of F is greater than the mean of G. We know that for certain, which is not following this thing. It must be less for F than for G. That means like F should be less than G. So it's not the mean, which is one of the options. So we know it's not the mean. They're trying to throw you off with that because the mean is changed, just it's brought further down in G. So G should not be the greater one. The median could change. It depends what the median was originally, and then if the value right below that was the same value, or the next value. Like we've seen some examples in previous problems where the median doesn't necessarily change, it could change. Which of the following must be less? And also again, it's less. So it's like G either has the same median or a smaller median. There's no way where G has a bigger median. So it also cannot be bigger. So neither of those. I was thinking they were going to say range, because the range would get bigger, right? G has a much bigger range, like the difference between the smallest and the minimum and the maximum value, or the standard deviation, right? Most of the measures are spread. The IQR is probably the same. Again, we don't necessarily know like what the Q1 is, what the Q3 is. Could shift based on adding another value. But likely IQR will stay pretty stable. Standard deviation will definitely change because it's like each value that's really far away is going to have a pretty significant effect on it. I guess we're just worrying about median and mean. It's neither of those two, so that would be option D. Just read carefully there. I think a lot of people would select mean, just thinking, oh, well, the mean will go down for sure. Yeah, but they're saying like which ones basically will go up, which is not. Dataset A consists of the heights of 75 buildings. So this is A, 75 buildings, and has a mean of 32 meters. So A, 75 buildings, the heights on average are 32 meters. Dataset B consists of the heights of 50 buildings and has a mean of 62 meters. So B is 50 buildings, I think this is very similar to the one from, I think, 2 questions ago, because there's also 75 and 50. They just, I believe, had different values for the means. 62 meters. Let's see if they ask the same thing. Data set C, okay, it's the same thing where they combine them. Data set C consists of the heights of 125 buildings, or of the 125 buildings from data set A and B. So you're combining A and B. What is the mean in meters of data set C? Okay, so the same thing, you could do it 2 different ways. You could weight them. So you could do 75 over 125 times 32 plus 50 over 125 times 62. And then it will just add up to the value you need. Or I think the more standard way you do it is figure out how many, like what's the total height of all of these 75. Like basically if you stacked all of those 75 buildings, it'd be 75 times the mean of each of those 75 is 32. And then you'd add that with 50 times 62. So the total height of the B buildings, so it's 50 times 62. And then you divide that by the total number of buildings that you have when you combine them all. So divide that by 125. All right, so I'm going to do the way that I wrote first this time. So it'd be 75 divided by 125 times 32 gives us 19.2. And then 50 divided by 125 times 62 is 24.8. So plus 24.8. And if you add those two together, just move the 0.8 to the 0.2, that becomes 20. 20 plus 24 is 44. That's what you get there. And then if we do it the more standard way, 75 times 32 is 2400, plus 50 times 62 is 3100, and we're still dividing that sum by 125. If you add those two together, it gives you 5500. So we get 5500 divided by 125, which is 44. Right? So either way you do it, you get 44 as your answer. So 44 is the mean. And just to check if it makes sense, right? It's between these two values, so that's good. And it's a little bit closer to A, which makes sense because there are more buildings that have that median, 32. So it should be closer to the one that's more represented in the combined set. Here we have a table. It says percent of residents who earned a bachelor's degree or higher, and different states. They don't say the state names, they just say state A, B, C, D, okay. A survey was given to residents of all 50 states. Well, it doesn't look like there's 50 values there. It only goes up to G, so what is that, 7 values? It's only 7. The residents of all 50 states asking if they had earned a bachelor's degree or higher. That's what this is here. And the results from 7 of those states are given. Okay, so 7 of them are here. It doesn't say if they're the highest 7 or anything. In the table above. The median percent of residents who earned a bachelor's degree or higher for all 50 states, so for all of them, was 26.95. And that was what, the median or the mean? The median percent. What is the difference between the median percent of the residents who earned a bachelor's degree or higher for these 7 states and the median for all 50 states? So you just have to find the median of the ones that are in this table and then compare it to this 26.95. So figure out basically what's the difference between those two values. Now, the trick with this one, I guess they're just the fact that they didn't list them in like increasing order. You go from smallest to biggest if you're going to find the middle value, because the middle of 7 is the 4th one, but this is the smallest one, not the middle value. So if we look, like the smallest value is this 19.5, so it's D, and then the next smallest is A, the 21.5 or 21.9, and then you've got 25.9, that's C. Then we have 27, which is B, 27.9, and then which is the 4th value, so we actually already know. And then E is 30.1. And F is 36.4, and the highest of these 7 is, oh wait, no, actually I messed that up. So F is the highest, 36.4, and G is the second highest. It's like that. So D, A, C, B, E, G, F of these 7. So the middle one is the B, and that would be 27.9. I'm just looking, right, there are 3 that are less than it, 3 that are greater than it. Just take that extra second to check. So your median value is 27.9. And we just need the difference between these two. And it looks like they're just under 1 apart. They're 0.95 apart, so that'd be choice B. And if you want to type in your calculator, feel extra safe, 27.9 minus 26.95 is, in fact, 0.95. All right, so that's how you do that one. Here we have Andrew and Maria each collected 6 rocks, and the masses of the rocks are shown in the table above. The mean of the masses of the rocks Maria collected is 0.1 kilograms greater than the mean of the masses of the rocks Andrew collected. what is the value of x? X is one of Maria's rocks. So Maria's rocks, we have, let's see, Maria, she's got x plus 3.1 plus 2.7 plus 2.9 plus 3.3 plus 2.8. And you're going to divide that by the number of rocks. That would give her mean equal to, I'll say the Maria's mean. We can't actually calculate that yet, but we can calculate Andrew's. And Andrew, the mean of Andrew, let's change this to say like mean M. Mean M equals this. Mean A would be the sum of all of his values and then divide by 6. And he has all 6 accounted for there. So 2.4 plus 2.5 plus 3.6 plus 3.1 plus 2.5 plus 2.7 divided by 6. 2.4 plus 2.5 plus 3.6 plus 3.1 plus 2.5 plus 2.7, 16.8. So we get 16.8 divided by 6. So the mean of these is 2.8. So that's Andrew's mean. And it says that Maria's mean is 0.1 kilograms greater than Andrew's. And this is in kilograms. So we just add it. So this is equal to 2.8 plus 0.1, which is going to be 2.9. And now if you want to find the total of Maria's, then you just multiply it by 6. So 2.9 times 6 gives us 17.4. So 17.4 is equal to, right, this numerator here. I basically just multiply both of these sides by 6, if that helps you. I like that. So we get 17.4 is equal to x plus 3.1 plus 2.7 plus 2.9 plus 3.3 plus 2.8. All right, so now, and again, that's just, I'm taking these values from here, just adding up all Maria's. I'm going to shrink it down so I have a little more space. So if I add up all of these values now, the ones that are not x, 3.1 plus 2.7 plus 2.9 plus 3.3 plus 2.8, give me 14.8. So x plus 14.8 is equal to 17.4. I can subtract 14.8 from both sides, or I can even think like what plus 14.8 give you 17.4. That would be x equals 2.6. So that's our value. And I guess to check it, you just plug it in here. Right? So we know if x is 2.6, then our mean of these should be 2.9. So we'd go 2.6 plus 3.1 plus 2.7 plus 2.9 plus 3.3 plus 2.8 adds up to 17.4. And then if you divide that by 6, it's 2.9. So it does check out. 2.6 would be our mass. And I think, let's make sure they didn't say to round it or anything. So just leave it as that. For a certain computer game, individuals receive an integer score that ranges from 2 through 10. Okay, so 2 through 10. And the table below shows the frequency distribution of the scores of the 9 players in Group A. So there's 9 players in Group A, that's here. And of the 11 players in Group B, so that's here. And the median of the scores for Group B is how much greater than the median of the scores of Group A? Okay, I mean, this seems pretty simple. Just go, right, well, the median of 11 terms will be the 6th term. You could think of that as 12 divided by 2, like 11 plus 1 divided by 2, or you go, all right, you need 5 players here, and then you've got your median is the 6th term, and then you've got 5 that are bigger than it. For 9, right, you could do that, it's the 5th term, because you'll have 4 that are less than it, 4 that are greater than it. So for this Group A, we need to find the 5th term. So we go 1, this is the 2nd, this is the 4th, and then this will be the 5th. And the 5th actually happens to be 5. That's not because it's the 5th, it just happens to be the case. Right? And then for this one, it's the 6th term. So 0, 0, 0, 4. 4 plus 2 is 6. So the 6th term is 6. It's also just a coincidence. It doesn't have to do with the fact that it is the 6th term, it just happens to be 6. So 5 and 6, those are the two medians. The median group score B is how much greater. So how much bigger is 6 than 5? That's 1. I feel like I'm missing something. That seems too easy. And that's the last question. Okay, perfect. I mean, I don't know. I guess it's not that. It's just kind of a weird way to present it. And I don't know why they shifted. Like, why is this so far down? They should have moved that up or something. Whatever. But, not too involved. Just make sure that you know what medians are and that you're accounting for the fact, like, the median will be the 5th term for this one, 6th term for this one. I don't know why they happen to make it like this, where the 5th term was 5, 6th term was 6 for the two different sets. But anyway, that seems like the main things you need to know are really understanding mean and median, how to calculate them, how they're affected by an outlier, how they're affected by shifting something up, shifting something to the right, or all of the data points. With mean, make sure that you can calculate what the total values are of if they give you the mean and the number of sets. So you're doing that mean calculation in reverse. I mean, if it helps, you could even write out the equation like mean equals like the sum divided by the number of things. If that helps you, then you can do it, or just, if you can conceptually do that without writing the equation, then it's fine. They do have a couple of these where it's like you're adding something in, like it affects the mean to this degree. So what is that value? Or you take this value out and the mean goes down by this much or up by this much. What would that value be? Just find the total with that included, find the total without that included, and then that change in total is accounted for by that value that was taken out. So that would be how you do that. This one's just testing, I guess, that to find the median, you need to put them in order. Just don't rush. I mean, if you look at this one closely, even just for like 2 seconds, you'll realize, all right, 19.5 is not the median because it's the only one that's less than 20 on here. But they could have been a little bit meaner if they put like 22 or something, or 25, like maybe you wouldn't check it. And let's see, 44. This one, yeah, it's another one where we're calculating like what the value this is when it's calculating the mean of a combined data set. So make sure you do that correctly. You can either weight it, which is the less common way to do it, but it works, or just find the total plus the total of the heights or whatever the thing is measuring divided by the total number of things when you combine the sets. You can't just do the mean of the two things unless they happen to have the same number of elements in them, which I doubt they'll do on the SAT. And here it's another one, how do outliers affect mean and median? Similar to the one from 2 before that. Make sure you understand how to read dot plots, how to interpret them. This one's just having to do it like if you shift something up, the spread doesn't change if you shift all of the points up, but it will move the central tendency up. So like the mean, the median, the mode would change. Not relative to each other, just like they're all going to move up by that same amount. This another one, like if this value is removed, then the mean changes to this. What was the removed value? This one, I think it's just testing if you can figure out this trick. Like it's pretty simple to just calculate the means given, maybe you have to make sure you know how to interpret like this kind of table, like what does frequency mean? That's how many times that term showed up. But I think, like, again, this one, they're just testing if you could quickly figure out that these means are all 85. I know it took a while to explain it, but if you could recognize that, you could do it in like a second. So this one would be really quick, when otherwise it would have been kind of tedious. And here we have a dot plot. And how does it affect the mean, the median? When you add in an outlier. Another one, calculate the missing or the value that's removed. Here, this one was kind of interesting, conceptually understanding if these are the two means, what does that mean about the medians? What does that mean about the minimum, maximum possible values for different things? Right, just interpreting like how could outliers exist without actually knowing what the data points are. This one, they're just trying to trick you with they added in the variables for the frequency, but since they all are multiplied by the same variable, it's just adjusted, like you just scale it up or scale it down. It won't really change how you do it. So you could treat them as 1 even if you want. This one was interesting too. So they had the histograms, and it looks like they're shifted up by 10, but technically it's saying like the smallest that could have been shifted that would still look like that is 1. So make sure watch this one if you haven't already, and if it's not clear, make sure comment that below. I can try to re-explain it, but hopefully that was came through clearly so that you understand how to do that one. Here, this one's kind of interesting too, just understanding like median as a concept, even with ranges of values. And there's another one, how are mean and median affected by removing a value, or is this one adding a value, so adding an outlier? It's a common concept they're testing here. This one, okay, I showed how you can do this with Desmos, and that's a useful tool to have in your toolbox. Like, make sure that you know how to do Desmos going in, if you have time to do so. But this one really you could have done without Desmos. Just make sure you understand what standard deviation is. You don't have to know how to calculate it necessarily. Like the fact that didn't show up in here at all, this would be where it would be. This is the hard section. But, understanding that if you add more values that are further away from the center, that's going to increase the standard deviation. So if everything else is held constant, but you moved what were close values to far values, it increases the standard deviation. It increases the spread. And make sure you understand box plots. There weren't that many box plots in here. There were a lot more dot plots than that. But just understand like this middle thing is your median value. This is your Q1, Q3, so 25th percentile, 75th percentile, your minimum, your maximum. So you can interpret it for range, you can interpret it for interquartile range. They didn't seem to ask that, but it helps to know it. And then they do ask about the median, so make sure you know that this will be the median. And just generally knowing what those box plots, those 5-point summaries represent. So remember, you'll probably learn them as box and whisker plots. Another standard deviation question. and just understand kind of what it is that has to do with the spread of the data around the mean. And this one was kind of interesting, being able to interpret these values and then you find the mean. I think you didn't really need to do all of this work. Again, you could have just recognized this one has a lot more values, like they get bigger and bigger as you go further down. This one gets bigger as you go up. So this one's mean is going to be smaller, this one's mean is going to be bigger. You can do that without even adding them up. So that's a trick to save you some time. Right, another one, calculate the mean, and here's your box plot from the beginning. So, again, just make sure you can interpret those. But yeah, if you have any questions, if you found an error or a comment or anything, put that in the comments below. I appreciate the feedback. If you found this valuable, make sure that you like, subscribe, promote more videos like this in your feed. So you'll see more math content, more SAT content, more of my videos. And yeah, other than that, best of luck with your preparation. And thank you for watching.